Hey y'all, it's Miss Johnson. Again, thank you for being there in class today and struggling with each other. Some days in math, it just feels like going to the gym and getting sore, which is good. That means it's working. So let's, I'm gonna go ahead and explain exactly what I meant to say in class, and maybe I said it in a different way, or maybe, whatever happened. I'm gonna go through this one more time on video so you can watch this in your own home. You can pause it, you can work alongside, and then tomorrow we'll get back in the saddle and hopefully it'll make more sense then. Also, thank you for the person that asked to make this video. I will make these just any day you want. So any day that it feels particularly confusing, reach out to me. This is a resource that you have that I can make these note videos pretty much anytime. Cool. Let's get it. Before we begin, before we talk about the two methods of simplifying radicals, let's name some useful facts, right? The useful radical facts are when we've got 3 to a power or any number to a power, and then we're taking the same root, these things cancel out. So effectively, 3 to the power 4 is some number, it's 81. And then the fourth root of 81 just turns it back into 3. So when these two numbers match up, we just get to cancel them and we get 3. So that's a really useful one because we'll section things up so that this happens a lot. The other one is whenever it's a square root, the thing that cancels is the power of 2, right? There's no 2 right here, but there's like an invisible 2. The square root is always a 2. And then whenever we have two things multiplied together, so if we've chosen to break it up in a certain way, or if these are two different bases, we can basically think of these as two mini problems, right? We can break these up into two separate roots. Let me make this more legible. We can section these up into two different radicals, multiplication, if we're multiplying or if we're dividing, and then we can cancel some of them, but not others, and we'll do that strategically. And then the exponent rules that we want to really hit on are when we have a power to another power. The way we combine those is we multiply those powers. So we have like 2 to the 4/5. And then when we're changing from exponents with mixed numbers, so like 3 and 1/2, if we're changing this to radical form, so this is exponential form. If we want to change it to radical form, like we do at the end of Dahani's questions, the whole number are the numbers not in the roots, and the fractions are the numbers in the roots. Again, so the fact there is x to the power n over m. That's awful. We'll use L. Is x and L. The root is always the bottom of the fraction in the exponent, and the exponent is always just the exponent. We keep it there. If there's no little number, that means it's 1/2. And if there isn't a little number, so like say if it's a 4, use a 4. Those are the rules we're going to use kind of over and over and over again. So screenshot that, write it down. Let's do it. We learned 2 different ways of simplifying these today. We called them Tia and Tahani, or more mathematically, simplifying something in radical form versus simplifying something in exponential form. The first thing we did, oh shoot, actually, this is my setup. So if we want to set up, and if we want to simplify, 2 to the 5th is 32. 32 times, what did I say? 864, geez. If we wanted to simplify 864, I know this is a big number, but we can do it. The first thing we would do is use a factor tree to break up the number into its prime factorization. For 864, this does look like I can divide it by 2, right? It's an even number. So let's do it. 864 divided by 2. I'm using my phone here. We get 2 and 432. Again, it looks like I can divide that by 2 because it's even. Divided by 2 is 2 and 216. That still looks even. So let's divide it by 2 again. That's 108. That looks even. Let's divide it by 2 again. Divided by 2. That's 54. That looks even. Let's divide it by 2 again. That's 27. That's no longer even, but we know that it's 3 times 9, and that 9 is 3 times 3. So this is actually a super long factor tree. But we had 864 ends up being 1, 2, 3, 4, 5 twos, and 1, 2, 3 threes. So first step is prime factorization. It might take forever. The cats are trying to eat my macaroni and cheese. Okay. Now we want to rewrite the problem with the factors. And this is what I had already done because I was trying to get ahead of myself. I do the square root. I do 2 to the 5th times, that's a 3. 3 to the 3. Now I'm going to look for groups whose size matches the root. What this means, we're going to do another one down here, is coming back up to this rule, right? When we've got a square root, and we've got a square, we can cancel those. When we've got 3 squared, we can cancel those. So I'm interested in rewriting this problem so that there's still 5 2s underneath the root, and there's still 3 3s underneath the root, but they're grouped where I can cancel some of the factors. So what I'll do is I'll say I can write this as 2 squared, and 2. So overall, that's still 1, 2, 3, 4, 5 2s, which is what we had up here. And then I'll write this as 3 squared times 3. We still have 3 3s underneath the square root, but I've sectioned them off so that 2 of them together and 1 of them is like a straggler. The reason I did this is because the square root and the square, I'm just going to, Step 4 says cancel the roots and the exponents that match up. So I get to cancel the square root and the square. I get to cancel this square root and the square. And I get to cancel this square root and this square. Move this down. And this is why we built these into patterns of 2, right? We looked for groups of 2, like 2 in the exponent, so that we could cancel it. And we know that square roots always cancel with 2s. These cancel, so it just becomes a regular 2. These cancel, it becomes a regular 2. This one didn't cancel, so we have to have square root of 2 here. This one canceled, it's a regular 3. This one didn't cancel, so it's square root of 3. And now the very last step is simplify by multiplying. We did 2 times 2 times 3. All the numbers outside of the root is 12. Nice. And then all the numbers inside of the root, 2 times 3 is 6. We've got our final simplified version. Great. Right? The other method that we learned how to use is the exponential method, right? The first thing we do is the same thing. We use the prime factorization. We use the prime factor tree to break things into the prime factorization. And again, the way you do this is you start with your main number and you just think of anything that would divide it, any 2 things. And you break it up into those 2 things. And then you just keep trying to break up these numbers into 2 multiplication things until you can't anymore. Now, whenever we rewrite it, instead of using radicals, we're going to use exponents. I should have used... because I want this one to be great. Now we're going to rewrite the problem with the factors and with the root as a fractional exponent. This root is a square root. So square root means the exponent is 1/2. So we're going to write 2 to the 5th times 3 to the 3rd, all to the power of 1/2. That's basically doing this, except in exponential form instead of in root form. Now we're going to use some exponent rules to simplify this. The exponent rule we're going to use is when we've got multiplication going on, we can basically distribute the exponent, and we can do that by multiplication. So this is 5 times 1/2 times 3 to the 3rd times 1/2, which ends up being 2. 5 divided by 2 is 2.5, so 2 and 1/2. And 3 times 1/2 is 1.5, or 1.5. Nice. And then when we rewrite in radical form, this is this rule up here, which is we take the whole numbers and we keep them out front. So there's 2 whole numbers for 2. And then there's a 1/2, and 1/2 always means square root. There's 1 whole number for 3, and 1/2, which means square root. And now we can simplify. 2 squared is 4 times 3 is 12. That's 2 squared times 3. And then under the root, we multiply the 2 things that are left over under the root, which is square root of 2 times square root of 3 is square root of 6. All right, if that's making sense, you're good to pause the video now and move on. I'll do one more example just for funsies, and I'll do it both ways. And let's make that black. Okay. For this question, for Tia's way, we've already got it in factored form in its prime factorization, and we've already rewritten the problem. So now for this one, for step 3, I want to write these in groups of 4. Look for groups of 4. What I mean by that is if we've got 5 3s, I want to write it as 3 plus 1 so that I can cancel these 4s. If we've got 5 10s, I want to write that as 4, well, 4 here, and then a leftover 2. Because 4 plus 4 plus 2 is 10. And then for the 6, I want to write it as a group of 4, and then a group of 2, which are left over, because 4 plus 2 is 6. So we have the same number of 3s, the same number of 5s. Oh, it's a 5, not a 4. That's the worst thing that's ever happened. Just kidding. There's much worse things. Nice. There's still the same number of 3s, there's still the same number of 5s, and there's still the same number of x's underneath the root. We just sectioned them into different parts. We're doing this so that we can cancel a bunch of them. We're going to cancel these ones, and cancel these ones. Anything we canceled just turns into the thing, the base that's been underneath it. And anything that doesn't get canceled is just rewritten. So the things that are canceled, we rewrite the base, and the things that don't get canceled, we just rewrite the entire thing. And now we get to multiply these things together. 3 times 5 times 5 is 75. And we've got an x, so 75x is outside of the root. And then we're going to multiply the things inside as well. Hilariously, it's the same. 3 times 5 times 5 is 75, and then there's 2 x's left over. So this is our final answer. Just these things next to each other. If I did this to Honey's way, I would say I want 3 to the 5th, 5 to the 10th, and x to the 6th, all to the 1/4, because we've got the 4th root. I would multiply I would multiply these exponents. I'm going to put them as mixed fractions. Two-fourths. And now I'm going to write them as radicals. There's 1 3 outside. There's 2 5s outside. And there's 1 x outside, because those are the whole numbers in our mixed fractions. 2 and 1. And then our fractional parts, the 1, the 2, and the 2, go underneath the 4th root, because all of them have 4 as a denominator. So we've got 1 3, 2 5s, and 2 x's. And then we'll clean this up a little bit by doing 5 times 5 times 3, and 3 times 5 times 5, which is again 75. Hopefully that makes a little bit more sense. Hopefully that's all the information all in one place. If you want me to make something more clear tomorrow in class, just let me know. I will post this video and this note sheet on Google Classroom. All right, cheers. See you tomorrow.